Hello everyone. Today I will present my working thesis towards semantic editing of volumetric video, a Gaussian splatting-based 4D segmentation method and evaluation framework. So in this presentation, there will be several parts. First, I will introduce the background, and we will see some state of art, and then the two main contribution of my work, and then I will give a conclusion. So first, I will introduce what is a volumetric video. The volumetric video is a next generation media content, unlike the traditional 2D video, which allows the user to see only the view captured by the camera. The volumetric video constructs the 3D space of a dynamic scene. So this is a 4D representation, which allows users to have 6 degrees of freedom navigation, including the rotation and translation. So with this 3D feature, there are many applications of volumetric video. For example, the immersive training, the sports streaming, or we can use it in the video game. We can have the virtual tuning. However, only the navigation in 6 degrees of freedom is not enough for the true immersive experience. We also need the interaction, just like what we have in the real world. So here I give an example of the interaction in the volumetric video. For example, here if a student is doing immersive training with a volumetric video, he wants to know a tool and to access the information of this tool. This can be done very straightforward in a game engine because all the objects in the game engine has the predefined information of the position and the semantic information. However, it's very hard for the volumetric video because this content is captured from our real world. So we need a 4D semantic segmentation to know where is the object and what it is. This need of 4D semantic segmentation motivates our thesis. So in this thesis, our objective, there are two main objectives. The first one is to construct a multi-view video segmentation dataset for training and evaluating the method. And the second one is to propose a 4D segmentation method to achieve some applications such as the 4D scene edition. For more detail, in our work, we focus on 3 parts. The first one is to do the annotation of the multi-view video dataset to have the ground truth masks for this video. And the second one is to propose a method to predict the segmentation masks. And the third one is to evaluate the method to get the score to measure its functionality. So let us go through what is volumetric video for more details. To produce a volumetric video, first thing is to capture the dynamic scene with the camera rigging. And then we can get the synchronized multi-view video data. With this raw input data, we do the modeling and analyze to get the volumetric representation. And with this kind of representation, we can get the rendered views from the VR headset or tablet to make the user have the 6 degrees of freedom navigation and interaction. So my work principally focuses on the modeling and analyze to do the segmentation. However, if we want to do the segmentation, the first thing is to know which kind of data we are using to present the scene. There are many kind of 3D data formats. For example, the bounding box, the texture maps, the point cloud, and some recent proposed presentation. For example, the radiance fields and the 3D Gaussians. There are some representations that can be produced by the normal view synthesis method. So in our project, we have chosen to use this kind of representation in our work. Why? Because in the volumetric video, we need some fine details rendering, and we need some representations to simulate some special materials, just like transparency and reflection. Here I provide a number of citations of these two methods. Since my thesis began on the October of 2022, and after that, we can see the method of NeRF and the 3D Gaussians has been cited very widely. So to better understand how this method function, we should know the reconstruction pipeline of this low-value synthesis method. In detail, we have the multi-view data captured by the camera rig, and then we do the calibration with some structure from motion method to get the camera parameters and the sparse point cloud. And these point cloud are initialized to this representation in the 3D space. And with this kind of representation, we can render the 2D images, and the 2D images calculate the differences with the input image and to optimize the volumetric representation. In this iterative training process, we optimize the parameters of these representations, and finally, we can do the rendering to new value of the scene, which has never appeared in the training data. So the most important part is to choose the type of the volumetric representation. As we have seen, that we have NeRF, we have 3D Gaussians. So which one is better, which one is most suitable for our work? We need to know their functionality. So here I will present some details about the narrow radiance fields. For example, here the NeRF, it uses the neural network to represent a 3D scene. We want to render a RGB image. We calculate the camera ray to trace the pixels on the image, and then we sample some 3D points along this camera ray. And these 3D points, which are presented by the position and the view direction, are passed into the neural network, and then we can get the color and the density. And then we have the volume rendering to render this color, to render the color of this pixel by accumulation in color and density of all these sampled points. Different from the NeRF, which use neural network that implicitly represent the scene, the 3D Gaussian splatting, it uses some 3D Gaussians explicitly represent the scene. For example, a scene is constructed by multiple 3D Gaussians, which has the parameters such as the centered color opacity and the 3D covariance. And we will want to render an image. Here, all the Gaussians along this camera ray, they are project or they are splatted on the 2D image plane. And when we want to calculate the color of this pixel, we calculate the contribution of all these Gaussians on this point. And here, for each point on the Gaussian, we can calculate its relative opacity and color, and we can get the final color of this pixel. So here I compare the two methods, the NeRF and the 3D Gaussians. We can see that they can both render the photorealistic scenarios. However, because the NeRF used the neural network to calculate the information of the 3D sense, so it needs more time for rendering and training. However, the 3D Gaussians is more explicit. The rendering is very straightforward, so it's faster in the training and the rendering. Even if the NeRF is compact because it only uses the parameters in the neural network, however, it is limited by its adaptability for the downstream tasks such as segmentation. So in our work, we have chosen the 3D Gaussian splatting to be our foundation 3D representation. Here comes the problem: how we can segment the 3D scene with the representation of 3D Gaussians. We have seen that the 3D Gaussians, it is a learnable representation which need the iterative training to optimize the parameters. It is not like some explicit representation such as point cloud or voxel. It can do the annotation directly. So here comes the question, how we can use the 2D data in supervision to optimize the segmentation of the 3D Gaussians. So to know the solution, we need to go through some state of art of the semantic segmentation from the image segmentation. So in the image segmentation, there are several types. For example, the semantic segmentation, which give each pixel a semantic label, and the instance segmentation, which can distinguish the different instances in the scene. And there is a fusion of the two, which is called panoptic segmentation, which give both the semantic label and also the distinguishing of different instances. In the past decades, the deep learning-based semantic segmentation method have been widely developed from the FCN to the vision transformer-based. We can see that there are very significant progress. There are more effective feature extraction, and we get better performance. And even now, we have some unified model to unify the semantic segmentation, instance segmentation, the panoptic segmentation in the same model. However, these classical segmentation methods has their own limitations, such as they depend on the training data set. They require the additional training for other work, and they are limited generalization. So to solve this problem, the researchers have turned to the foundation vision model. Thank you for the vision transformer. So the vision foundation model is we can call it a big model. It is trained by the massive diverse data. For example, the text, the images, speech, or other data format. And the model is represented by the large-scale parameters. It can be adapted directly to the other downstream tests, such as segmentation, classification, or text-image alignment. So here I give some example of the vision foundation model. For example, we have an input image. If we put this image to the Dino, we can get a very representative image feature. We put this to the clip, we can get the open vocabulary classification. And if we put this image to the segment anything model, we can get this segmentation directly. So we can see that there are some benefits of this vision foundation model. For example, there are zero shot or few shot. We do not need the extra training. They are open vocabulary. They are not limited by the training data set, and they are very flexible to use. So with this kind of powerful model, the researchers in the have tried to put these features to 3D segmentation in the 3D Gaussians. So how does this work? The parameters of the 3D Gaussians, we add a parameter which is called the feature embedding F, just like a parameter of color. When we do the rendering of the 3D Gaussians, at the same time of the rendered image, we can render some features. And these features are optimized. So here we achieve the 3D segmentation based on 3D Gaussians. Since the 3D Gaussian has been proposed, there are many methods. They are developed for the 3D segmentation, developed based on 3D Gaussians, mainly for two kind of tests. The first one is open vocabulary segmentation, and the second one is the pure object segmentation. So we can see that the features of the vision foundation models are widely used in this kind of method. So you can see that we have achieved the 3D segmentation. They have the spatial consistency. However, for our test, the 4D segmentation, we also need the temporal consistency. To have the temporal consistency, we can pass to the video segmentation. The video segmentation is an extension of the image segmentation. For example, there are two branches. The first one is about the semantic segmentation. They have the tracking of the objects along the timeline, and they provide the semantic information. However, they suffer the same limitation that they are very dataset dependency. The second branch is the video object segmentation, which focus only on segment the objects, but they lack of the semantic information. However, in our work, we have chosen to use the video object segmentation because now with the help of the vision foundation model, the semantic information can be predicted directly by these models without training. So we only focus on the tracking of the objects. So here I give an example of the video object segmentation. Given the video frames and the initial masks, we pass this mask and the frame to the model, and then we get the mask of the other frames. And this is also called the mask propagation. So here we can see that we have the image segmentation as the multi-view extension is the 3D segmentation, which has the spatial consistency. And for the multi-frame extension, we have the video segmentation, which has the temporal consistency. However, for us, our goal is to achieve the segmentation in volumetric video in the 4D space. So we need both spatial and temporal consistency. However, there's a gap in this research domain. So our goal is to fuse the two kind of segmentation in the same work. So after review the state of art of the segmentation methods, we are now going to find out how to achieve the 4D segmentation. The first thing is to choose the best data set for training and evaluation the method. There already exist several multi-view video data sets that has the annotation. However, they are limited by the scenarios. There are not enough categories. For example, in the dataset in the KT family, they focus only on the street view, and for other dataset, they focus only on the foreground person reconstruction, and they do not provide enough annotation for other objects. So this is not suitable for our work because we need to reconstruct the real world of all the environment, including the foreground objects and other small objects in the environment. So we decide to propose our own data set. The first thing is to collect the data. We have collected 17 scenes, which of diverse themes, including sports, daily life, or street view, and they are captured by different types of the synchronized camera rig. And there are some complexity in the scenes. For example, the human-object interaction, or they are always occluded. This dataset is used for training and evaluating the 4D segmentation method. So the ground truth of the mask also need to be a spatial temporal consistency. So here I give an example of this feature. In a scene, when we segment an object, we give the identity and the semantic label, and these labels need to be tracked through different views and through different frames. They should be always the same. So this is called spatial temporal consistency. To achieve such annotation for the whole multi-view video, to annotate frame by frame and associate the mask manually is very cost and time consuming. So we propose a semi-automatic annotation strategy. So here in a multi-view video dataset, we have many cameras. We select the one camera is called the initial camera, which capture the most of the objects. The first thing is to do the manual annotation and the correction on the keyframes of the initial camera. And then we apply a special mask propagation method of this camera to propagate the mask to other camera views. And then we apply the temporal propagation of all these keyframes in each video to have the segmentation masks of all the frames. So in detail, the first step is to do the mask spatial propagation. Here we can define the initial camera and the camera near, which has the view very similar to the initial camera, and the camera far, which capture the scene has a significant difference with this initial camera. So here, if we apply the video object segmentation method, the XMM, which is a state of art method, to the near camera, we can see that the quality of the propagation is agreeable. However, if we use the XMM directly from the initial camera to a camera far, we can see that there are many errors because there are significant difference between the two cameras. To solve this problem, we have proposed a method of the key point matching. For example, in the initial camera and the camera near, we do the key point matching of each instance, and then we do the triangulation to project all these match the key point to the 3D space, and then we have the 3D point cloud with the different category, and then we do the projection of this point cloud to the camera far. However, this time we project the bounding box. So where we project the bounding box, because we can use the segment anything model to segment the different instances with the bounding box. This is a vision foundation model which can be used by just click on the instance or just give the bounding box of the instance. So here we can see that the result of this method is much better than the propagate directly the mask to the camera. So this saves us much time for manual correction. And then once we have all the mask on the keyframe, we do the propagation, we do the mask propagation temporally with the same model. Here we can see that we only propagate the different person. Why? Because in our data set, we have defined different type of objects, the environmental objects, static objects, and dynamic objects. So in the data set, when we do the annotation, we annotate the environmental objects and the static object only on the first frame. So we can treat the dynamic objects for the other frames. They save the time. And then it's also solve a problem that when we do the annotation of the static objects, the occlusion appeared here by the static objects and dynamic objects can be solved directly. So with this semi-automatic annotation strategy, we have annotated our data set, which has 3 annotated views per scene and totally 459 instances and 73 categories. And you can see that the objects in the different views, they are well presented by the same color, meaning that they are spatial temporal consistency. So as the dataset proposed, there were no 4D segmentation methods. So to show the usage of our dataset, we decided to evaluate the 3D segmentation method. So we create a sub dataset, use our real world dataset, which we choose 12 scenes and 50 objects of 4 different types. The domain object, which is always the biggest, the forward object in the scene, and the occluded objects, some small scale objects, and the object with some complex structure. So this is a 3D segmentation benchmark to evaluate static segmentation. Here we compare our object with other existing 3D object segmentation benchmark. For example, the involved spinner, which was widely used by evaluating the 3D segmentation method. You can see that in such data set, they have annotations only on the foreground object, and the objects are always the dominant one. They do not have other type of objects. And for the left mask, they have the annotations of different types of the objects. However, they have only 3 scenes, and they are all indoor scenes. So we can see that our object is more generalized. Our dataset is more generalized for 3D object segmentation. And then we have evaluated the 4 different segmentation methods based on NeRF and 3D Gaussians on our real-world sub dataset. We can see that even they have got a very good score on other dataset. However, they cannot have the good score on our dataset. For example, the ISRF is a object level segmentation method. They are struggle to treating the segmenting the small objects. And we have found that the method Gaussian grouping proposed in 2023 has the best performance on this 3D segmentation benchmark that they can handle all types of objects. So here is the contribution of our first part. We have proposed the spatial temporal consistency annotation. We have construct the data set, a novel evaluation metric, and a new benchmark for the 3D segmentation method. And with the proposal of the data set, now we need to propose for the segmentation method with this data set. So now we have finished the first part of the work, and now we are going to do the second one and third one. So we have seen that there are many 3D segmentation methods based on the 3D Gaussians and the NeRF. However, if we want to achieve the 4D segmentation, if we do it by the 3D segmentation frame by frame, there will be some problem. For example, there is no temporal discontinuity, and there will be a problem of the stockage of the representation. So to solve this problem, the solution is to use the 3D segmentation and the 4D reconstruction together. Here we can see that in 3D segmentation, there are always feature embedding to represent the object or semantic information. So we can integrate this feature embedding into the 4D reconstruction. And then we can achieve 4D segmentation with the temporal continuity, and this use less storage. So for the 4D segmentation method, there are many choices. Finally, we have chosen the space-time quotients, which use the polynomial functions to present the moving of the quotients and the change of the opacity, because this is a method which has the parameters in the polynomial functions, and is very lightweight and portable. So we decided to propose the method that fuse the 3D Gaussian splatting, the 3D Gaussian grouping, which got the best score in our dataset, and the space-time Gaussians. So here I will first present the details of the Gaussian grouping, the 3D segmentation method. Here we can see that they add object feature into the attribute of the 3D Gaussians, and then to optimize these features, they use SEM to select the target objects and use a video segmentation method, which is called the DIVA, which was proposed in 2023. That was the state of the art at that time, to propagate directly the mask to other cameras. And then the Gaussian grouping can render the mask, and that can be calculated the difference between the input mask and the render mask. Here there are three types of loss. The loss of the image to calculate, which is proposed in the 3D Gaussian splatting, which aim to optimize the initial parameters. And there are two loss: the loss 2D, the loss of the rendered mask and the provided mask, and the loss 3D to do a regularization of the 3D Gaussians with the same label. So in our case, we have the input is a multi-view videos. So we propose the space-time Gaussian grouping, the method which fuse Gaussian grouping and space-time Gaussians. So here we have the multi-view videos to optimize the 4D reconstruction. We need to add some temporal parameters that's proposed in the space-time Gaussians. Here I put the color in yellow, and also the feature proposed in the Gaussian grouping, the object feature. So in order to optimize these parameters, we can calculate the rendered image with the input images that has been done in the space-time Gaussians to optimize the temporal parameters. However, for the object parameters, we need the special temporal consistent mask. So based on the mask of the spatial propagation, we reuse the video segmentation method on all these masks to do a temporal propagation. So here we have the spatial temporal consistent mask as supervision that can be used to calculate the difference between the rendered mask and to optimize all these parameters. So as the proposition of this method, the Millward dataset was not published. So we decided to create a new benchmark based on our Millward dataset to evaluate our method. Here we have selected 16 scenes, and we do a new annotation of 90 frames on the test view. And there are 3 different instances per scene. And there are main actors, up-to-date objects, some small-scale objects, and some frequently moving objects. And this is regarded as a complementary to the Millward dataset. So for the evaluation, for the initial view, we select the target objects with the segmentation anything model, and we propagate these masks spatially and temporally, and we will calculate the masks on the test view. Here, the test view is not used in the training model. So this evaluation is very fair. We have compared our method with 2 other methods. The first one is the Gaussian grouping. This is the static object segmentation method. So we apply the Gaussian grouping on 10 different frames, and we calculate average score. And the other one is another 4D segmentation method, which is called the SA4D. It's also based on the 3D Gaussian splatting and the 4D reconstruction. So we can see that our model has achieved the best score in the intersection over unit, and we have gained training time compared to the 2 methods. Even though the size of the final representation is a little more than the SA4D, however, we do not need the extra neural network to decode the moving of the 3D Gaussians. So our method is more portable and is more it has more adaptability for other applications. So based on our 4D segmentation method, we have some application. The first one is the 4D scene edition. Here we have done work of the recolor of the target objects. You can see that the different instance in this scene is recolored to the yellow, red, and green, and the color is always the same, spatial temporally. And the second one is the application is to achieve the interaction in the VR. Here in the scene of the medical training, we can select the different instance by the segmentation, and they can provide the semantic information when we choose the instance. So here in this part, our contributions is to propose the 4D segmentation methods. We have created a new benchmark for evaluating, and we develop a multi-platform viewer in the 4D space to do the navigation and interaction, and we have captured the 3-in-1 analytical training scenes. So to conclude this thesis, we have 2 main contributions. The first one is to propose the real-world dataset, which has the spatial temporal consistency annotations. There are some limitations, such as we still need some minor operations of the annotation, and they are limited labeled fields. The second main contribution is to propose the space-time Gaussian loop method to achieve the 4D segmentation list, to achieve the 4D segmentation. However, there are also some limitations, such as when we do the training, the quality of the masks used for supervision need to be improved. And now this method is suffering from a high computational cost for long video. So for the future work, I think for the segmentation methods or the interaction in the volumetric video, it is just in the first stage. So we need more annotated data sets to include more diverse scenes for training the methods or evaluating methods. And we also need some efficient storage and training strategy for this method. If we want to apply the 4D segmentation methods on the applications such as the sports streaming or some long video reconstruction. And the third one is a perspective for the 4D segmentation. Now we see that we have segmented the objects spatial temporally with the masks, and the scene is reconstructed and represented by 3D Gaussians. However, we have only the object feature. We have only the identity of different objects. We do not have the physical meaning of objects. So in the future, maybe we can integrate the physical meaning for each segmented object as the we have the semantic information. And finally, in the future, maybe we can achieve the 4D foundation models for the semantic scene editing. Like now we have the segment anything model for 2D images. We just click on the image, we can segment the things. However, in the future, maybe we need the foundation model in the volumetric video. We do not need pre-train of the segmented mask. We just need to click on one object and we can do the interaction and edition. And here are some publications in the past 3 years. So thank you for your attention.